Hi there, Mr. Holcomb here with another episode of the Math Behind the Modules. This is lesson 3, writing products as sums, sums as products. The opening exercise says to solve problems using a tape diagram. A sum of money was shared between George and Benjamin in a ratio of 3 to 4. So that's George to Benjamin. George has 3, Ben has 4. If the sum of money was $56, how much did George get? So if I were to do a tape diagram, and I drew this out like this, there's 3 equal pieces, and then I do the same for Benjamin. I draw out a tape diagram for his, and it's 3 equal pieces. Well, Benjamin is 3 to 4, so I'm going to have to add one more piece of tape to his, so it's 3 and 4. Then the question is saying, how much did George get? George is this amount, so that's the question. Okay, but I do know that the sum of the two is $56. Okay, so the way we can look at this is we have 7 squares, or 7 units, equals 56. So since I have 7 units and it equals 56, in order to find out what 1 is, I would divide 56 by 7 and I would get 8. So 1 unit equals 8. Okay, so now I know that this is 8, that is 8, that is 8, and so on, and so on. And that's what a tape diagram means. Every single piece is equivalent amount. Okay. So 8 times 4 is 32, 8 times 3 is 24, 32 plus 24 is indeed $56. Okay? So the question says, how much did George get? So that's the question. Well, here it is. So 3 units. George has 3 units of the 7. 3 out of 4, or 3 to 4 is 3 out of 7. So if 1 unit is 8, 3 units is 8 times 3 equals 24. Okay, so that's $24. So George received $24. Benjamin didn't ask, but Benjamin was 8 times 4, or $32. Okay, all right, example 1. Represent 3 plus 2 using a tape diagram. Okay. There's 3, plus 2 more, so this is 3, this is 2, and that's a total of 5 squares. Okay. Represent x plus 2 using a tape diagram. Okay, this one's a little bit different. We don't know x, so let's make that a bigger, different sized, obviously different sized rectangle than the unit amounts that we do know, which is 2. So this is 2, because this is worth 1 and that's worth 1. And this one is x. So x plus 2 is some unknown plus 2. Okay. Note that the size of the units that represent 2 in the expression x plus 2. Using the size of these units can predict the value x represents. Okay. So in this example that I drew, you could estimate this. So since this distance is 1, there might be a 1 there, and there, and there, and there. And it looks like x is approximately 5, maybe. Okay. That's just an estimation. Okay, now it says draw a rectangular array. That's something we haven't done. Think of it as a tape diagram, but it's more specifically designed to show length and width. Okay, so what that means is we have, let's think of this as multiplication. And if we had a rectangle, the area of a rectangle is length times width. So if the length was 3, right here, times the width, 3 plus 2. So in order to represent that, I could do, okay, this would represent the 3 here in the parentheses, and then I need 2 more to represent the 2 right here, and I will shade those in. Okay, so there's 3 plus 2. Well, the 3 outside just means times 3. 3 times this sum. So that means I want to go this way, and I want to do that 3 times. So there's to be times 2. If I do it one more time, then I have my model complete. Sorry for the mess. Okay, and this is going to be shaded, and that's going to be shaded. So it's 3 plus 2 times 3. Okay? So this is equal to 3 here. Alright, so now it says draw an array for 3 times the quantity x plus 2. Now remember what I did before in the prior example with x. I can make x bigger to show that it's more than the other 2. Look at that. So there's x, and this is 2. Okay, and it's times 3. So I'm going to duplicate this 3 times. Make that line supposed to be equal. Okay, so there's my 2, and there's another x here, and then finally a third 2. So now that I'm done, this means times 3. This is an array for the quantity 3 times the quantity x plus 2. So if I multiplied that, if I distribute, how many x's are there? 1, 2, 3 x's. 3 times x is 3x. If I multiply 3 times 2, I get 6. 1, 2, 3, 4, 5, 6. Okay. Okay, key term, distributive property. So that's what I was just explaining here with those lines. The distributive property can be written as the identity A times sum B plus C in parentheses equals AB plus AC for all numbers A, B, and C. So what we're doing is we're taking A times B, that's just simply AB. You keep the sign, it's in between, plus, and then A times C is right here. So we're just multiplying both terms by that A. That's a distributive property. So if I distribute it up here, I would get 3x plus 6. 3 times x, 3x. 3 times 2, 6. And I definitely have 3 x's and 6 ones. Exercise 1. Determine the area of each region using the distributive property. Okay, so in order to find the area of this larger piece, it's 11 times 16. Okay, so let me represent this. It would be, you have to realize that this whole distance is the sum of this plus this. Okay, so I'm taking the width, length times the width. It's just like doing area. Okay, so if I want to do it in parts, this would be the same as saying 11 times 16 plus 5. Okay, because 16 plus 5, this whole side over here obviously is that 21. If this is 16, this is 5 more, it's a total of 21. So I can find the total area of all of it, which it didn't ask for. It said determine the area of each region. But I can find the total area as well. So in order to find the area of each region, we're going to use the distributive property. We're going to take 11 times 16. Well, 16 times 10 is 160. plus 16 more is 176. And then 11 times 5 is 55. So this area is 176. This area is 55. And when I add those two, 6 plus 5 is 11, carry a 1. 7 and 5 is 12, plus 1 is 13, carry a 1. And that's going to be a total of 231. Now if I take 11 times 21, which should be the same answer. And sure enough. Okay? So it says determine the area of each region. 76 for this big piece, 55 for the small one. Example 2. Draw a tape diagram to represent each expression. Okay. X plus Y plus X plus Y plus X plus Y. Alright? Well, if I made X this size, I have one there, I have one there, and I have one there. It's a little too small. Okay. And then if I have a Y, let's just say Y is 1. So let's make Y a rectangle. So all the green rectangles are equal. Okay. So I have an X plus a Y, an X plus a Y, an X plus a Y. So there is a diagram to represent that expression. Okay. It's not asking to solve, it's not asking to combine, it's just saying represent. Okay, so now I have 3 X's, so if X were this size, make 3 of them, plus, actually I don't need the plus I suppose. Okay, and then I want to represent Y as something different. So how about a rectangle about this size? And I need 1 plus another 1 plus a third. So this is X plus X plus X, Y plus Y plus Y. Okay. 3x plus 3y, I could either do as I have already done down up here. I could repeat this. Again, bring this down here. So I could just repeat that. Like such. Okay, because that's 3x, that's 3y, so it means the same thing. Or I could draw it like this. I could say, here's x, here's y, and I need 3 of them stacked up. So I could do it as an array. Okay, where this is 3, and this is x. Okay. I label this x, 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 y, y, y. 3 times the quantity x plus y. So I could then repeat this here, but just show it without the breaks. So this is my piece here, and this is my y's here, where this is 3. This is the length x, and that's the length y. So this would give me 3 times length times width, length times width. Okay. Example 3. Find an equivalent expression by modeling with a rectangular array and applying the distributive property to the expression 5 times the quantity 8x plus 3. Okay, so I can just simply make a rectangle. Okay, could then make a smaller piece. This, call that 3. The length here is 3. The length of this is 8x. And then finally, the width is 5. So in order to find the area of this, it's 5 times 8x, or 40x. And 5 times 3 is 15. Okay? They are not like terms. So 5 times 8x plus 3, I can't add 8x and 3. They're different. This has a variable and a coefficient. This is a constant. They're non-like terms. I cannot combine them. So I just simply distribute. We get 40x. 5 times 3 is 15. Okay, now we can substitute in any number we want. I always avoid 0 because that's the additive identity. And I always avoid 1 because that's a multiplicative identity. So it's not a good way to check using the identities. So I could pick any number. For example, I could say let x equal 5. Okay, and then I take 5 times 8x plus 3, and it should equal 40x plus 15. So I'm going to substitute in 5. So I'm going to put a 5 everywhere I see an x. So I'm going to rewrite this as 5 times 8, and then I'm going to put a 5 here, plus 3, equals 40 times 5 plus 15. So that's going to be 5 times 40 plus 3. PEMDAS or GEMDAS says to do grouping first. So I got to do inside here first. Then inside is multiplication and addition. Multiplication comes first. Then I add. Okay. And then 5 times 3 is 15. Carry the 1. 5 times 4 is 20. Plus 1 is 20. Over here, 5 times 40 is 200, plus 15 is also 215. So I plugged a value in and proved that the distributive property is true. Exercise 2. For parts A and B, draw an array for each expression and apply the distributive property to expand each expression. Substitute the given numerical value to demonstrate the equivalency. Okay, so the 2 would be our height, and then this would be x. This would be 1. Okay, so 2 times x is 2x. 2 times 1 is 2. So we get 2x plus 2. Then it says plug in x equals 5. 2 times 5 plus 2, 10 plus 2, 12. Okay. Again, the number outside is our height, 10. Then we're going to call this piece 2c. And then we're going to call this piece 5. 10 times 2c, 20c. 10 times 5, 50. 20c plus 50. Plug in 1. 20 times 1 plus 50, or just 20 plus 50, 70. Okay? So there's an array solving using the distributive property. Alright, for parts C and D, apply the distributive property, substitute the given numerical values to demonstrate equivalency. So now they're saying to use the distributive property instead of the array. Okay, so now we do 3 times 4f, which is 12f. Positive times a negative is negative. 3 times 1 is 3. Substitute my f in, so I'm going to put 2 in place of f. Give me 12 times 2 minus 3. Okay, order of operations says to multiply first. 12 times 2 minus 3, and I get 20. D. Positive times a negative. Always deal with your sign first so you don't get that wrong. Positive times a negative is 9 times 3, 27. Then just put the R. 9 positive times a negative, negative. 9 times 11, 90. Substitute in our R. Okay, so we're going to get negative 27. Replace R with 10. Subtract 90. Negative 27 times 10 is negative 270 minus 99. That's really close to 100, so you do mental math here. 270 minus 100, negative 270 minus 100 is negative 370. But we're off by 1, so it's going to be negative 360. Okay, notice what I'm doing here, by the way. I'm distributing, I'm substituting, I'm simplifying, I'm solving. I'm expecting everybody to do all of these steps. Don't try doing it in your head. When you do a homework assignment, when you do a quiz, when you do a test, you always do the work, substitute, simplify, and solve. Example 4. Rewrite the expression 6x plus 15 divided by 3 in standard form using the distributive property. So I would write 6x plus 15 divided by 3. Okay? Well, we can't divide, so we're going to, distributive property is multiplication. So I'm going to change that to times. And I'm going to take the inverse of this, because we have a rule. If we divide by something, we can multiply by its reciprocal. So I'm going to multiply it by 1. So if the number's outside, it doesn't matter if it's in front or if it's in back. We can still distribute it, just go this direction. So it's going to be 1/3 times 6, which is 6 over 1, x, plus 15 over 1 times 1/3. I'm just distributing to both. So this 3 will make that 6, a 2. 1 times 2 is 2 over 1 is simply 2. Or 6 divided by 3 is 2x. The x stays. And then this 3 will make that 15, 5. 5 times 1 is 5, divided by 1 is 4. So the answer is 2x plus 4. Exercise 3. Rewrite the expression in standard form. Standard form is just a simplified form where we don't have any more like terms to combine. So the first thing I'm going to do is rewrite this as 2b plus 12 times the reciprocal of 2, which is a half. I'm going to distribute 2b times a half is 1b. 1/2 times 2 is 1. Plus, distribute 12 times a half is 6. So the answer is b plus 6. Okay, more examples. The first thing I'm going to do is rewrite 20r minus 8. I'm going to change that division to multiplication. I'm going to change the 4 to a quarter. I'm going to distribute. 20 times a quarter is the same as 20 divided by 4, which is 5. R just stays. A negative divided by a positive is negative. And a quarter times 8 is 2. Okay. 49g. 49g minus 7 times the reciprocal of 7. Distribute. 49 times 1/7 is the same as 49 divided by 7, which is 7. G, negative divided or times a positive is negative. 7 divided by 7. 7. Example 5. Expand the expression. So all we're doing is distributing. Okay. So I'm going to get 4 times x, which is 4x, plus 4 times y, which is 4y, plus 4 times z, which is 4. Exercise 4. Expand the expression from the product to a sum by removing grouping symbols, using an area model, repeated use of the distributive property. Repeated use of the distributive property is simply going to be, first rewrite the problem. Okay. And then show 3 times x plus 3 times 2 times y plus 3 times 5 times z. 3 times x is 3x. 3 times 2 is 6 times y. 3 times 5 is 15. X, y, z, 3 different terms. They are not alike. I cannot add them. This is. If I were to do this as a model, an array, then the number outside is your width. Let that equal x. Change colors for y. So let's make y a little bit bigger because there's 2 of them. So let's call that 2y. Okay, in other words, that would be y, and that would be a y, so there's 2y. Okay. But I'm not going to show that middle piece. I'm just going to call that 2y. And then z, there are 5 of them, so I'm just going to make this a larger rectangle. I'm going to call that 5. If I do the area one at a time, 3 times x, 3x, 3 times 2y, 6y, 3 times 5z, 15z. Add the 3, they aren't like terms, so we can't add them, we just put plus signs in between. This is our algebraic expression. Example 6. A square fountain area with side lengths S. Side length S. Side length S. Is bordered by a single row of square tiles as shown. Express the total number of tiles needed in terms of S 3 different ways. If this is a 1 foot by 1 foot square. So we could pick out a value. We could just choose a value for this. So how about I just trace this sort of, okay, and then move it. So there's one. And if I copy it, paste it, and then I move it, so again, I move it, okay, there's another one. And we just keep doing this. Okay? How many are we going to need to finish? This is not cool. Oh, there's 2 there. That's okay. I'm going to stop here, though. So you have to take into consideration one other thing. So if I have 5 here, then I would have 5 here. And I'd have 5 here. I'd have 5 here. But that does not account for my corners. So in all actuality, I'd have 5, 10, 15, 20 plus these 4. Okay? So how would I represent that as an equation? Each side is the length of 7, isn't it? Okay. So if this whole side is 5, and then these 2 corners make 7, the whole thing, all of it is 7. So all of this is 7. So area is length times width. The whole thing is 49, but it's not asking for area. It says express the total number of tiles needed in terms of S 3 different ways. Okay, so I could say 5 or 4S times, let's say that. Well, if each tile is 1x, I could say 5x plus 5x plus 5x plus 5x plus 4x, for instance. 5, 10, 15, 20 plus the 4 corners. Okay, that's one. Or I could combine them all and say 4 times 5x okay, plus 1x for each corner. So 4 times 5x is 20x, and 4 times 1x is 4x. And then finally I could combine those and say 4 times 6x. Okay. So really what we're doing is, if I took a piece that was this, which is 6x, notice I'm not using the corner here. They're going to overlap or go right to the end here, but not right to the end. So we are going to get 4 rectangles of the same length. Okay. Could come up with that. That'd be 6x times. Alright, that's the end of this lesson.